Welcome once again to this class. Our topic today is gravitational fields. Gravitational fields. If you remember that we talked about fields, that it's a region where a certain force is being felt or experienced. A region where a force is experienced depends on the kind of force that is being experienced in that region. When a gravitational force is being experienced in a certain region, it is called a gravitational field. If it's an electric force that is being experienced in that region, it is called an electric field. And if it is a magnetic force, it is called a magnetic field. Now, gravitational field. Before we talk about gravitational field, let's talk about how masses on Earth relate with each other and also with the Earth itself. Somebody will ask, whatever goes up surely comes down, basic law of gravity. The Earth has its own pull, which is Earth's pull. How does this come about? Within the limits of experimental errors, it is discovered that if two masses are close, M1 and M2, that there is a force of attraction between the two of them. There is a force of attraction between the two of them. Any object on the Earth's surface, there is always a force of attraction between two objects. If you put a spoon in your kitchen and you put a pot, the two of them, there is a force of attraction. A car has a mass of a body, and the person walking by the side of the car, there is a force of attraction between the car and the person, because they are two bodies of different masses, assuming them to be M1 and M2. But the question you ask yourself is, I've been standing by side of cars several times, but I've never had that attraction. I've never experienced that force. The reason why you don't experience that force is because of these masses are considered to be negligible, in the sense that your mass is small, that of the car is small when to compare with the complete mass of the Earth, where both you and the car is present inside. Now, when you as a person or a mass of a body inside the Earth's surface, the Earth has a mass. Let's assume this is the mass of the Earth. And you are on the surface of the Earth. You have this your mass. This is your mass, M1. And that of the Earth is M2. Because the Earth is far bigger than you will be attracted towards the Earth. The Earth will not be attracted to you. The Earth will not come to you. You are the one that comes to the Earth. So when an object is inside the Earth, when you throw the object up, the object will be attracted towards the Earth. That is where the force of gravity comes from. So that force of gravity is naturally the attraction between the mass of the body on the Earth's surface and the Earth itself. But between two smaller objects, there is a force of attraction. But it's just that that force of attraction is negligible. So you don't actually experience it. You don't know that such force exists. If two buildings are standing side by side, there is a force of attraction between them because they are bodies of masses. But the thing is, because their masses are still negligible when to compare with that of the Earth, you will not know that there is an attraction between them. So there is force of attraction between any two masses that is close to each other. But for the earth, because the earth is massive and so big, that force of attraction between you and the earth will be felt, and you call it gravity, and that whatever goes up surely comes down. Now when you consider that of the moon, for example, the moon does not have that kind of mass as the earth. The earth is far bigger. But the moon, when you get to the moon, you like I will use the word, you don't actually need a table on the moon. Probably you don't need a table. I make jest of that once in a while. When you put the gravity on the moon is less, far less. Now, previous classes we talked about it, that gravity on Earth is gravity on moon divided by 6. So the acceleration that the gravity on Earth will cause is 9.8 meter per second square, and that on the moon will cause is 1.67 meter per second square. So you can see that the force of gravity is far higher on Earth than in the moon. So if you are in moon, if you have a plate of soup with you, before you drop it on the table, you have to force the plate down, because the force that will pull the plate down naturally is very low. So you have to pull it down. So, but on Earth, you just hold it, it goes. But on the moon, you have to push it down. That's the difference. So the gravity there is low. So when you are walking on the moon, you tend to force your leg down as you're moving. You raise your leg, you force it down, because the force of gravity that will naturally pull you down is very low. So now, the reason is because of why is this gravity low is because of the mass of the moon is smaller when to compare with that of the Earth. So what it means is that the bigger the body, the higher is gravity. So you cannot experience it between bodies around you, because your body, your mass, and the mass of those bodies are negligibly small. So you cannot experience it. But that it does not exist, it does exist. So ladies and gentlemen, let's continue with this. Now, the gravitational field, we're going to explain gravitational field using Newton's rule to explain it. Now, let's start from here. We're going to state our law with respect to force of attraction between two masses. So we'll start from there. So the law states, that this force of attraction is directly proportional to the product of their masses. What masses are we talking about? M1 and M2. So if it's the product of their masses, what we'll be having is that this force of attraction is proportional to M1, M2. We can assume that. But inversely proportional to the square of their distance apart. So the law states, the universal law of gravity states that this force of attraction is directly proportional to the product of their masses. but inversely proportional to the square of their distance apart. So when someone asks you, state the universal law of gravity, you say, the universal law of gravity states that the force of attraction between two masses is directly proportional to the product of their masses and inversely proportional to the distance apart between the two. So automatically, if you are having M1 and you're having M2, there is a force of attraction between them, but there is a distance, they have a distance apart. So most time I'll represent the distance apart as capital letter R. You can also represent it as small letter r. Good. Now, so F is directly proportional to M1, M2, the product of their mass, product multiplication. Now, but the same F is inversely proportional to their distance apart, to the square of their distance apart. What's the distance apart? Their distance apart is R, capital letter R, and the square of it. That's where the word comes in. Square of their distance apart. So now I have two statements. So from here I can merge the two of them together to get F is equal to M1, proportional M1, M2 over R squared. Now, the direct variation is at the top. The inverse is beneath. So this gives me what we call a joint variation. Good. Now, F is equals to K M1 M2 over R squared. So this K is called the constant of proportionality. Constant of proportionality. Now, this constant of proportionality have a value. K is equal to G. K is equal to G. So therefore, F is equals to G M1 M2 all over R squared. So please, you are going to take note of this first. The force of attraction is equals to G M1 M2 divided by R squared. So this is the first mass of the first body, and this is the mass of the second body, because these two bodies, they have a force of attraction between each other. Now, but in this case, you ask a question. What's the value of G? You say G is gravitational constant. So anytime you see the value of G, you just say it's gravitational constant. So it is the constant used to represent the gravitational value, G. So gravitational constant is G, the first mass is M1, the second mass is M2, and the distance apart is R. Now, from there, we can continue to talk about this. What about a situation where the body that is being attracted is a body that is inside the Earth's surface? This body that is inside the Earth's surface, let's assume this is the Earth. Capital letter N is the mass of the Earth. Let's use that to represent. But the body is inside the Earth, small letter m. In this situation, we're going to have the Earth and this body. They are going to attract. But the body will have to move towards the Earth. The reason is because the Earth is bigger, but there is a force of attraction. So for a body that is inside the Earth's surface, like you, like me as a mass of a body inside the Earth's surface, F is equals to G M 1 M2 all over R squared. So if this is G, M1 will represent the mass of the Earth, capital letter M, while M2 will represent the mass of the body that is inside the Earth, which is small letter m, divided by R squared. So you first keep this. This is for a body that is inside the Earth's surface. So that's where capital letter M comes in and small letter m comes. So this is the mass of the body that is inside the Earth. It can be a cup, a spoon, it can be anything, a car, aeroplane, whatever. But that body is inside the Earth's surface. But the Earth itself is capital letter M. That is its mass. So with the Earth, a body being inside the Earth, there must be a force of attraction between them. That force of attraction is capital letter F. So, and this is the body that is inside the Earth. And their distance apart is r squared. Thank you. Now, from there, we can move on to discover that in a situation where we now consider the weight of a body, what gives the body weight? The weight of a body. In our previous class, we talked about weight of a body. Weight of a body is the earth pull on the body. That force of gravity exerted on the body is what gives the body the weight. It's the earth pull on the body. So now I can consider the fact that weight is equals to force and is equals to energy, mass times gravity. So therefore, I can operate this value to replace this. I will now have mg from here to be equal to g cap letter m over r squared. Looking at it, the same mass of body we are talking about, you cancel that. So what will be left with my g? So my g is going to be capital letter G, capital letter M, all over r squared. So this is what relationship between r and g. From this equation, you observe as a good student from your theoretical questions that r squared is inversely proportional to g. Because when you dismantle this equation, for example, what you get out of it is that g is directly proportional to capital letter M. As M increases, g also do what? Increase. As M is increasing, g is increasing. And here, as g is inversely proportional to r squared, meaning that as g is increasing, r is decreasing. If r have to increase, g must have go down. They are inversely proportional to each other. Now, from here, this is the relationship between g, m, capital letter M, and r. Now, class, it's easy. From there, we'll talk about something else that is very important. It is called gravitational field intensity. Gravitational field intensity. How strong? What is the intensity of the gravitational field at that point? So the strength of that field at that point defines the gravitational field intensity at that very point. How strong is that gravitational field? How the bodies feel it? How do you feel? How strong you feel that gravitational field? So the intensity is the strength of gravitational field at a particular point. Now, it is defined as force per unit mass. It's defined as the force. It is defined as force per unit mass. So therefore, gravitational field intensity, which is represented as G, is equals to force over M as gravitational field intensity. But from here, we can do some other math. If you scatter this equation, you will have F times 1 over M, which is correct. So from here, I can get something like this. What is F again? What did we get as F? F is Gm, small letter m, r squared. So that will give us G now to be equals to Gm, m over r squared times 1 over m. So this will cancel this. So G2 is G cap m over r squared. So you can use any of this formula to calculate gravitational field intensity. Gravitational field intensity is F over m, and it's also gm over r squared, which is the relationship between g, m, and r. Please, it is measured in what? It is measured in force. It's measured in Newton per kg. Newton per kg. Newton per kg. Newton per kg. That's the value. Okay, now, that's that. We'll talk about something else. Let's see how gravity varies with height. Let's see how it varies with height. Relationship between gravity and height. Okay, you are somewhere in there, okay, probably when you are somewhere sitting down on the ground, and when you climb a very tall building, or probably when you are inside in an aeroplane and you are far high above there, how does gravity vary with height? That's what we want to consider next. So let's see the relationship between gravity and height, how it varies, whether it reduces or increases. Now, gravity and height. That is variation of gravity with height, h. Let's see how gravity can vary with height. Gravity can vary with height in the sense that, if we recall that G is equals to G m over r squared. So this is at its ground state. Take note of that because of your questions. At its ground state, G is gm over, that's when you are sitting on the floor, you are not moving. You are just there, that's gravity, ground state. But by the time at height h, G now becomes gm over r plus h up squared. It's another thing entirely. So at the height h, this is the value of G. At the ground state, this is the value of G. So if a body automatically is at a higher, if you leave ground state to a higher ground, you will observe that your gravity, that height will be added to r. So the value r plus h in mathematics is bigger than r alone. No matter what h is, no matter you add what, anything h is going to give to you, that thing is going to be added to r. So that will make r plus h to be greater than r. So because of that, as a body, r plus h will be greater. So because of that, you have g m divided by this. So and as this value gets greater with a square, if you divide this with this, it's going to cause this to reduce. So this is the value of h at a height h. This is greater, so when you divide this with this, the value of this surely will reduce. Because as told you initially, this is inversely proportional to this. As this is increasing, this will be decreasing. Now you've added h to it, so it has made it bigger. So as it's getting bigger, the value of G surely will be coming down. But if G is increasing, these have to decrease. Anything that causes these values to decrease, this value will have to go up. Inverse proportionality. So now we have that. Let's now consider something else. What about a situation where you are inside the earth and you need to take something out of the earth? You need to fight your way out of the Earth's gravitational field. The Earth's gravitational field itself sometimes can be a nuisance. It has its importance. Whatever goes up comes down. You need fruits. When fruit grow in a tree, they fall down on their own. Sometimes you don't need to climb up. It has its importance. But it also has its disadvantages. One of its disadvantages is that for you to take a body out of the Earth's surface, you need to fight against the Earth pull, which is force of gravity. Even the aeroplanes are designed in such a way that they have to battle with coming out of fighting against gravity, escaping gravity. The rockets are built to escape gravity. That is why if you look at the rockets, you see that they are made of streamlined bodies. They are streamlined. The aeroplanes are streamlined so that they can penetrate easily. An aeroplane that is built that has a face that looks like this, an aeroplane is built and the face looks like this, you cannot compare it with the one like this. This will escape faster than this. So this is a streamlined body. So it constitutes a nuisance for you to take a body from the Earth's surface out of the Earth's gravitational pull. That now brings us to something that's called gravitational field potential. A potential naturally is a work done. The work done in taking a body of mass m out of the Earth's gravitational field, to escape out of the Earth's gravitational field, is called gravitational field potential. That is to move it from that point where it was initially to the point where you now need that body of mass m is called gravitational field potential. It is a work done. Now, you're right. The gravitational field potential is the work done in taking a unit positive charge in Coulomb's law to that point. And in gravitational is the work done in taking a unit mass from that point to escape the Earth's gravitational field. Now listen. It's given as V is equals to minus Gm over R times M. Now the question is, where do I get my minus sign from? My minus sign is from the fact that a body that is against gravity, it is minus. But when it is for gravity, it is plus. So minus Gm over R times M, that is negative sign because it is working against gravity. So the gravitational field potential is the work done in taking a unit mass from one point to another within the Earth's gravitational field, or from that point to infinity. So also in Coulomb's law, when you hear is the work done in taking a unit positive charge from one point to that point, it's still the same thing. Good. Now from there, so you have V is equals to minus Gm over R times M. So it is a work done. So always remember that. Minus Gm R M. Good. Now, in that situation, you could discover that this value, because it's work done, it's measured in joules because it is work done. So anytime you do take a calculation on this, there's work done and it is measured in joules. Now, that will bring us back to something else that has to do with, now that we've done work to take a body of mass from the Earth's surface to that point that is needed, that body must have moved with a certain velocity. and that velocity at which it moved at that time is called escape velocity. So we will calculate escape velocity from here. Now take a look at this. Now, escape velocity. Now, for your escape velocity, it's simple. It is possible at a point when V is equal to kinetic energy of movement. So when V is equal to kinetic energy of movement, this is V, which is work done. So that is, and the kinetic energy of movement is also work done. Energy can neither be created nor destroyed, but can be converted from one form to another. At rest, potential. Moving, kinetic. So this is kinetic because you have a situation where work done is not equal. The work done, which is gravitational field potential, which is work done measured in joules, is now equal to the kinetic energy of movement of that body that you are moving from the Earth's surface to that point. Now take a look at this. They will give you gravitational field potential becoming G M over rho m is equals to half mv squared. So that will relate us back to the fact that this m cancels this. So we're having G m over r is equal to v squared over 2. If you cross multiply this, what you get is that v squared is equals to 2gm over r. So that v is equals to square root of 2gm over r. This is what we'll call escape velocity. So when you are calculating your escape velocity, you can always use this formula to calculate escape velocity, which state that v is square root of 2gm over r. And you see the way I take my deductions, you can easily take it. Even if you forget the equations, the formula, it's still easy for you. Just remember that gravitational potential is equals to kinetic energy of movement. So this is equals, from here you obtain your equation. I always say to students of physics that don't bother so much about the formulas, bother how the formula come to be, and it will stay with you. Now, from here, we'll continue by saying that, oh, there's something else we can do. But we'll remember that G is equals to Gm over r squared. We remember that. So if I cross multiply this, what will Gm become? Gm becomes Gr squared from this now. So if I decide to replace Gr squared with Gm here in this equation, what happens? So I just replace Gr squared, I replace it here as Gm. So that will now give me V is equals to square root of 2Gr squared over R. So one arrow goes here, one arrow. What will be left is one arrow. So V now will be square root of 2Gr. So that's the second formula for calculating escape velocity. So escape velocity can be this, and escape velocity can be this, which is V is 2G, square root of 2Gr. And escape velocity is square root of 2Gm over r. Put that down. Now, it's not over. There's something we just talked about. It's lithium. It's not much, but it will be our last subtopic on gravitational field before we go to questions and answers. Now, that is what we call you have what we call the orbits, the satellites. For example, you want to shoot a body out of the Earth's surface. Maybe you want to put a satellite on the space. There's a lot of satellites in the space. When you shoot a satellite into the space, you need to do a lot of calculations. Calculations you do, you have to know the escape velocity out of the Earth's gravitational pull. You need to know the gravitational field potential of that particular body. You need to take all the calculations into consideration. Now, from there, we want to see how we can estimate velocity of orbits of satellites if shot into the space. Now, take a look at this. Now, velocity now, there's it. If a satellite is shot out of the Earth's gravitational field and is to stay there or remain there or reach the point where it's to be positioned, you have to consider two values. The first value you're going to consider is that there is a force that keeps the Earth moving around, and that force is called gravitational force. And that force on the outside for rotation is related as what we call centripetal force. Now, the centripetal force of a body that is moving around like the Earth, the centripetal force is mv squared over r. Let me use capital letter R because I've been using capital letter R. So let me use capital letter R. So this thing you see is called centripetal force. It's a force that moves the Earth round. Like the days of my forefathers, they used to believe that some very big giants, heavy giants, they are the ones that push the Earth round. But that was not true. What pushed the Earth round, what keeps it to move round, is called centripetal force. Now, in further advanced analysis, we'll discuss centripetal force in details with respect to mass conversion and weightlessness. Now, force is mv squared over r, is centripetal force. Now, for me to attain that velocity that I actually need, I will need to consider the fact that this same force is equals to g mm over r squared. I'll consider that. I'll have to consider this. And I will also consider that this same force is equal to mg, mass times gravity. So if I consider these, I will have to put them together. So therefore, these forces are the same. So because of that, I will say mv squared over r is equals to mg. So if m cancels m, what will be left with me is something of this nature. And that will be m cancels m. So if I cross multiply, I have v squared over r is equals to g. So if I cross multiply, I have v squared is equals to gr. It depends on what I want. So, but V will give me square root of GR. That's the satellite velocity, or the velocity of the orbit. That's the satellite velocity or the velocity of the orbit. So if you want a satellite to stay, you must calculate the value of G and the value of the radius. So by the time you take the 12 and take the square root, you know what will fit the satellite to remain at that particular position and stay. If not, it will fall back. Like the several cases that was tried during the Apollo case. Now, we're done with our deductions. We're going to take few questions on this topic, gravitational field intensity.